Hey everyone, so welcome to our next unit on moles, and in today's lesson we're going to go through just kind of what moles are and how to convert into them, how to count and use them in terms of our calculations when we go through some quantitative analysis. So basically it starts off and it says we live in a quantitative world, and quantitative just means quantity or amount, and so oftentimes we measure things by count, or by its mass, or by its volume. So we can say things like 3 for $2.40, for instance. So something by count. Maybe by weight, if it's $1.29 a pound, or if it's by its mass, if it's like 279 per kilogram. Or it could be by volume, where we're talking about $12 a bushel for something. So overall, we've got these three different ways that we can go through and kind of count things in, kind of an everyday situation. So when we start to kind of see this kind of problem, we actually don't need any prior knowledge to do it. What I'll do is I'll get you to read the question, and then just see if you can come up with what the answer is on your own before I kind of show you the steps that we would go through in terms of kind of figuring this out in a quantitative way. So pause the video and give it a try. Alright, so the video itself, or the question, sorry, says, what is the mass of 90 average size apples if 1 dozen of the apples have a mass of 2 kilograms? So, what we're looking for is the mass of 90 apples in kilograms. And there's probably a couple of different ways that you've gone through and have figured this out that will likely look a little bit different than the way that I've set this up. The way that I've set this up is kind of by design. It's to help us go through and get into the chemistry side of things, but overall we can take a look and see kind of if you end up with the same answer overall that I'm going to get down here. So if we start off with wanting to find the mass of 90 apples, I need to use a ratio to start with. So we have this ratio here that says 1 dozen apples has a mass of 2 kilograms. So that's a ratio that I can use. And the way that I'm going to set up this ratio is I'm going to say for every 2 kilograms is a dozen apples. But then we have this counted value that we know. We know a dozen apples really means 12 apples. And I would like to find out how much weight 90 apples is. So this dimensional analysis piece in chemistry is really helpful for us to do unit conversions. And so I want to kind of show you just what this kind of represents or looks like. So if we multiply this out, we know that if we multiply fractions, so if I had like 2 over 3 times 3 over 5, hopefully you can see here that this works out, because when we multiply the tops and bottoms together. So 2 times 3 is 6, and 3 times 5 is 15. Now between 6 and 15 I can make this smaller because 3 goes into each of them. So if I divide this by 3 and divide this by 3, then really I'm left with 2 over 5. Now this is just kind of going through and showing you some stuff with fractions. But overall, do you see that if I have a number on the top and a number on the bottom, they can cancel each other out? And what am I left with? I'm left with 2 over 5. So it saves me that step of reducing this at the end. So if I have something on the top and something on the bottom, then I can cancel them out. I can reduce them because 3 divided by 3 is 1. So here, in our example, I have a dozen apples on the bottom for a unit and a dozen apples on the top for a unit. So my dozen apples are going to cancel top and bottom. And then if I look at what I have left here, I have kilograms per apple. So it's 2 kilograms over 12 apples. But I'm multiplying it by 90 apples, because that's how much I wanted to know. So my apples units are actually going to cancel out as well, and what's the only thing left over is kilograms, which is what I'm trying to solve for. So whenever there's not a number written in a fraction sense, like this is 90 apples, this is really just over 1. And so we treat this the same way when we multiply fractions. We multiply the tops together, so we do 2 times 1 times 90, and then we divide that by the bottom, or 1 times 12. So 2 times 90 is 180, and then 180 divided by 12 equals 15, and then my only unit left over is kilograms. So 15 kilograms is the average mass of 90 apples. And likely you were able to get to the 15 in a different way, but it's this dimensional analysis piece that's going to pop up as we go through this chemistry unit. So let's start off and go through the idea of what is a mole. So similar to how specific numbers of things like apples can be grouped and quantified, chemists use a unit that specifies a number of particles. So the idea of the mole is that mole of a substance is 6.02 times 10 to the 23 representative particles, which we're going to see is just called representative particles of a substance. And the SI unit for measuring the amount of a substance. So a mole, by definition, which unit is just MOL, is 6.02 times 10 to the 23. Now what that's saying is that every object, if I can quantify it, a mole is nothing more than an amount, the same way that a dozen represents 12. So a mole just happens to represent an extremely big number, right? Remember this times 10 to the 23 really just means take this decimal and jump it 23 places to the right. So here's where using your calculator is going to become really important in being able to punch in the right numbers with scientific notation to still work out to get the right value at the end. So we'll give a little bit of time at the while we go through some practice problems here to kind of go through your calculator and make sure that you understand how to punch in the correct value to make sure that you're getting the right answer. And if you get stuck, just let me know. So a mole is nothing more than an amount. Just like a dozen means 12, a mole means 6.02 times 10 to the 23. So this number is pretty special, and it's called Avogadro's number. It was named after the Italian scientist who helped to clarify the difference between atoms and molecules. So a molecule would be something like H2O, whereas an atom would say we have 2 atoms of hydrogen and 1 atom of oxygen in the molecule H2O. So there's a really good video, and I'll post it on the video section that I would really encourage that you go through and watch by Tyler DeWitt, and he just goes through and does a good job giving an introduction into moles in terms of giving you a framework as to what they stand for. So I really encourage that you go through and watch this video when you get a chance. So kind of moving on or continuing on, and if you want to pause it here and then watch the video and come back to this video, that might help as well. So a representative particle refers to atoms or molecules or formally units that's present. Remember, it's just a placeholder like dozen means 12. So most representative particles are just the atoms themselves. So iron, for instance, is composed of iron atoms. The diatomic molecules, which we have from before from our list, so I2, H2, N2, and so on, and other molecular compounds have these representative elements that are the molecule itself. So just special situations or special circumstances. For ionic compounds, the representative element is the formula unit of the compound, CaCl2. And a mole of any substance contains Avogadro's number of representative particles, or it contains 6.02 times 10 to the 23 representative particles. So if I had 1 mole of something, depending on what it's talking about, I'd have 1 mole of sulfur would mean that I would have 6.02 times 10 to the 23 atoms of sulfur. So let's go through and converting particles to moles. So there's a little bit of an equation here that I would really encourage that you copy down, because it will help as you go through and start this converting process and being able to convert particles into moles. So if I want to know moles of something and I have representative particles, I'm going to have to multiply it by 1 mole on the top over 6.02 times 10 to the 23 representative particles on the bottom. And remember, representative particles could be atoms, could be molecules. It just depends on the context of the question. Okay, it takes 6.02 times 10 to the 23 of something to be classified as a mole. So, as an example, how many moles of magnesium is 1.25 times 10 to the 23 atoms of magnesium? So, the way that we would go through and set this up, I've got 1.25 times 10 to the 23 atoms, and I want to see how many moles this is. Now, if I had 6.02 times 10 to the 23, then I would know my answer would be 1. This number is smaller than that, so I'm going to expect my answer to be smaller than 1. So, let's go through and just kind of see what this looks like. So, I want to see moles of magnesium. Okay, moles of magnesium. And then we had 1.25 times 10 to the 23 atoms of magnesium. And then we're going to multiply that by our ratio that we have. Now I have atoms of magnesium on the top part here, because remember this is like a fraction. Okay, it can be written over 1. And then I'm going to multiply this so that atoms cancels out and I'm left with moles. So if atoms are on the top, then atoms need to be on the bottom here. And our atoms in this case represent our representative particles. So I have 6.02 times 10 to the 23rd atoms of magnesium, and it takes that many atoms of magnesium to make 1 mole of magnesium. So top and bottom are going to cancel, atoms of magnesium, and I can see in this case that when I multiply, I'm just multiplying by ones, but I'm going to have to divide these numbers, right? Number on the top divided by the number on the bottom. So 6.02 times 10 to the 23 is on the bottom. That's the number that you're going to be dividing by 1.25 times 10 to the 23 on the top. So take a second on your calculator and make sure that you know how to use it. Make sure that you can divide these numbers accurately to get the correct answer. And the number that you're looking to get is 0.208 moles of magnesium. So let's see if you can work out on your calculator to get to that point. And again, if you have questions, please let me know along the way. So I'm going to pause this video for part 1, and we'll pick it up in part 2.